Here's a oscilloscope clock that I built up, which I think is kind of a cool thing. What it does is it's a kit that allows the oscilloscope to display an analog clock face on it. And it does this using vector graphics techniques that are kind of similar to some of the original vector graphics video games that came out in the early 80s. That didn't use a raster scan type technique like a normal television would do. What this kit does is it actually takes the white spot of the oscilloscope and moves it around directly to various points on the screen very rapidly to paint an image on the screen, in this case a clock. So it's kind of a cool use of an oscilloscope that normally is just kind of sitting there not doing much most of the time. And it has some really cool features on it. So I'll show you the actual circuit boards that are driving this display. Let's get the camera up here. So here's what we've got. This is the circuit board I bought from a place called Sparktronics on the web, www.sparktronics.com, I believe. It's a pre-assembled kit, so I really didn't have to put anything together because it uses all surface mount technology. But it has a power connector here. It's got RS-232 input and output. It's got a real-time clock chip built onto the board that's backed up by this the small button cell on the circuit board. It has channel 1 and channel 2 and ground outputs. You can solder VNC jacks into these positions here, but I'm just clipping onto the test points on the board at this point. And the two buttons here can be used to access the various clock functions, and there's hundreds of different combinations of displays, including digital and binary clocks and things like that, that can be displayed on the oscilloscope face itself. One of the cool things is this LED here, which I have configured right now to actually play the time in Morse code. So even if you don't have a scope hooked up to it, you can look at the LED, and if you're a ham radio operator or no international Morse code, it actually continually spits out the current time in Morse code. Kind of an interesting feature of it. Now normally the clock, the time on the clock is driven directly from the real-time clock chip on the board, but there is an option for it to receive data from a GPS board. So what I've done is I've taken this old Motorola GPS board, Encore board, probably late 90s type technology, but it still does exactly what this board needs to function. And I've got the GPS board interface through this little 10-pin connector and ribbon cable directly into the clock. And what this does is it uses this small GPS antenna through the radio input cable here, the antenna connector. When it locks onto enough satellites and gets a good lock, it starts outputting a series of text strings that are sent over this cable into the board where it's soldered on, and the microprocessor then interprets those text strings, and it uses those to automatically set the clock based on satellite time. So it's extremely accurate when it has a lock on the satellite. Now the GPS board also puts out something called a 1 PPS signal, 1 pulse per second. And the rising edge of that pulse is extremely accurate, and it's synchronized to the time that's sent on the text via RS-232 to the board. So once the clock is set, those very accurate pulses that are coming out of the GPS board once per second drive the advancement of the second hand. And theoretically it's accurate to within a couple hundred nanoseconds, maybe even less, something around 50 nanoseconds, depending on how you have this board configured. So I used a program called Win Encore that's was put out by Motorola to program this to put out the correct format and the correct frequency rate. It actually updates the time every 5 seconds to keep the load on the clock board microprocessor fairly small. And it really works well. I'm really happy with the performance of it. Just going back to the clock display quickly, you can see on the very top, just under the digit 12, there's a letter G that flashes every 5 seconds. In fact, it's not now because I don't have the antenna near a window. So I'll put the antenna closer to the window where it can get a lock. When it does receive a GPS signal, it flashes a G for GPS every time it receives an update message from the GPS board. And the way I have that configured, that occurs every 5 seconds. If the time that the GPS board is sending it doesn't match its internal real-time clock, it will do the update and flash the G rapidly to indicate that it's doing an update. There you can see it's achieved the lock again. So the net result is that it keeps a extremely accurate time. And just to show some of the other capabilities on it, this is the menu. It's possible to put the dial into from the analog mode into a digital mode. That displays a standard digital clock. Put that back to a 24-hour face. It also has some other cool modes, including an RS-232 terminal mode. And we'll change the application to terminal. And here you can actually see the strings of data coming in from the GPS board. Those are standard strings that most GPS units are capable of putting out. So to reset it, we'll go back into the clock and reset the application type to clock. So kind of a cool use of an oscilloscope and having it interfaced. There you can see it's updating after I was in a different application. It's flashing, and now that it's synchronized, it'll just flash a G every 5 seconds to indicate an incoming GPS scheme. I've checked this against some other timing references that I have, and it is extremely accurate down to about 100 nanoseconds or so. So kind of cool use for an oscilloscope that's kind of sitting there gathering